Welcome to this lecture on the fast and epithermal neutron spectrum in nuclear reactors. In this lecture we will derive the expressions for the energy dependence of the fast and epithermal neutron flux density in light water reactors. My name is Jan Leen Kloosterman and I work at the Faculty of Applied Sciences of Delft University of Technology in the Netherlands. First we will sketch the main processes of neutrons in thermal reactors. Neutrons are released in fission events with an average energy of about 2 MeV. We call this region the fast energy range. By means of elastic collisions with moderator nuclides and inelastic collisions with heavy nuclides, neutrons can reach the epithermal energy range, sometimes also called the resonance region, in just a few collisions, after which the energy of the neutron has fallen below the threshold energy of the inelastic reaction. In the resonance region, neutrons can lose energy via elastic collisions with the moderator nuclides, or they can be absorbed in the resonances of the fuel nuclides, uranium-238 for example. The neutrons that survive absorption will eventually reach the thermal energy range, where the neutrons have a kinetic energy comparable to that of the moderator nuclides, or they can leak out of the reactor core. As a consequence, neutrons can lose energy in a collision, but they can also gain energy, and we call this downscattering and upscattering. Eventually, after a number of collisions, the thermal neutrons will be absorbed in the fuel or in the structural materials of the reactor core, or they can leak away. Part of the neutrons that are absorbed, either in the thermal range or in the epithermal range, will initiate new fissions, which will lead to the release of new fission neutrons, and the cycle starts all over again. Neutrons are produced in fission events with high energy, usually in the MeV range. The energy spectrum of fission neutrons can be described by two distributions. One is a Maxwell distribution with an artificial temperature of 1.6 times 10 to the 10 Kelvin. And the other one is a Cranberg fission spectrum, shown in the lower formula on this slide, which contains an exponential function and a sine hyperbolic function. On this slide, you see the two spectra as a function of the energy of the fission neutrons. The black line is a Maxwell distribution, and the cyan line is a Cranberg fit. The scale of these two lines is given on the right axis. For comparison, I have also plotted the fission cross-section of uranium-235, the red line, and of plutonium-239, the blue line, as a function of energy. It's clearly seen that the fission cross-sections have rather low values in the fast energy range above 100 keV, but much higher values in the thermal energy range below 1 electron volt. Therefore, in nuclear reactors, we want to moderate fission neutrons as quickly as possible to the thermal energy range, where they can easily induce new fission events. The most probable energy of the fission spectrum is around 700 keV, indicated in the plot with the solid brown line, and the average energy is around 2 MeV, indicated with the dashed brown line in the plot. Here you see the fission spectrum again, but now with a linear energy axis. It's clearly seen that the high energy tail continues to very high energy, which is the reason that the average energy of the fission neutrons is about 3 times higher than the most probable energy of about 700 keV. Using the formula of the Maxwell fission spectrum, we can easily calculate the values of the most probable energy and of the average energy of the fission neutrons. From the lecture on the thermal neutron spectrum, we know that the most probable energy of a Maxwell-Boltzmann distribution has a value of 1/2 times kT, where K is Boltzmann constant and T is the temperature, while the average energy is 1.5 times kT. From these expressions, the values for the most probable energy of the fission neutrons becomes around 700 keV and of the average energy around 2 MeV. Now we recall a result from a previous lecture. It's about elastic scattering of neutrons with a non-moving target nucleus. If we have a neutron with energy E, it can scatter to any energy between alpha E and E with equal probability, but it cannot scatter to energy below alpha E. Here, alpha is a ratio of A-1 and A+1 squared, with capital A the mass of the target nucleus expressed in units of neutron mass. If the target nucleus becomes lighter, the energy range of the scatter event becomes larger. Hydrogen, for example, has an alpha value of 0, and the scatter energy range is the whole interval from E till 0. But if we have a very heavy nuclide, uranium for example, the energy range over which a neutron can scatter becomes very small, and a neutron needs many collisions to slow down from the fast energy range to the thermal energy range. Now we look into detail at the small energy interval dE' around E'. If we have no absorption and only scattering with hydrogen, the collision density of neutrons at energy E' can only be due to neutrons that have scattered at a higher energy E. The general expression is given on the top line of this formula and reduces to the expression on the second line for scattering with hydrogen. Only in that case the value of alpha is 0. Here we see the result from the previous slide again. It is easily verified that the solution of this neutron balance is given by the formula in the second line on this slide, which says that the neutron flux density behaves proportional to the inverse of the product of the scatter cross-section and the energy E. If the scatter cross-section is constant, the result becomes very simple. In that case, the neutron flux is proportional to the inverse of the energy E only. This is the background of the so-called 1/E neutron flux density in the epithermal energy range in light water moderated reactors. Of course, the 1/E neutron flux density is only valid if the scatter cross-section is constant. For hydrogen, this is actually a very good approximation for a wide energy range from 0.1 electron volt to 10 kilo electron volt, as shown on the slide. In reality, a small fraction of the neutrons being moderated from the fast energy range to the thermal energy range will be absorbed by the nuclides in the fuel rods, like uranium. In this plot, I've shown the neutron capture cross-section of uranium-238, which is dominantly present in the fuel. Compared to the scatter cross-section of hydrogen, indicated here with the solid red line, the capture cross-section of uranium has a low value, except for the peak values of the resonances. In the following slides, we will calculate the probability for a neutron to be absorbed in one of these resonances of the fuel nuclides. To simplify the derivation, we will neglect leakage of neutrons and we will assume that the resonance at energy ER has a rectangular shape with the width of delta ER, as shown in the plot. Furthermore, we consider only scattering with hydrogen. The probability for a neutron that scatters at energy E to be absorbed in a narrow resonance around ER is a product of the probability to scatter within delta ER around ER, which is a ratio of delta ER and E, and the probability to be absorbed at ER, which is a ratio of the absorption cross-section and the total cross-section at energy ER. The resulting expression for the probability is shown on this slide. This is however not yet the final result, because we should also include the neutrons that have scattered multiple times before they are absorbed at ER. This will be done on the next slides. Now we will calculate the probability for a neutron to be absorbed at the resonance after one intermediate scatter event between E and ER. The probability of the neutron to scatter once between the initial energy E and the resonance energy ER is the ratio of the energy interval between E and ER and E. Once the neutron has scattered at E1, the probability to scatter to the resonance energy ER is equal to the ratio of delta ER and E1. As on the previous slide, this should be multiplied with the ratio of the absorption cross-section and the total cross-section at ER to get a complete absorption probability. The final result is given in the second formula on this slide. Note that the average value of E1 is E plus ER divided by 2. We can continue this process to calculate the contribution of neutrons that have scattered twice between the initial energy E and the resonance energy ER. After a neutron has scattered once, the probability to scatter to energy E2, somewhere in between E1 and ER, is given by the ratio of E1 minus ER and E1. The probability to scatter to the resonance energy is now given by the ratio of delta ER and E2. And a complete expression is shown in the third formula on the slide. Note that the average value of E2 equals E1 plus ER divided by 2. On this slide, I've summarized the expressions till now. P0 is a probability for a neutron that scatters at energy E to be absorbed at the resonance at ER without any intermediate scatter event. P1 is the absorption probability of a neutron that has scattered once in between. P2 is the absorption probability of a neutron that has two intermediate scatter events. And P3 for a neutron that has 3 intermediate scatter events, etc., etc. Note that each probability can be written as a product of the previous probability and a factor that changes slightly from one to the other. The differences are indicated with the red circles. In short, the probabilities can be written as P0, shown here on the top line, and the recurrent relation for the absorption probabilities of neutrons that have scattered in between, indicated with the second formula on this slide. The total absorption probability is the sum of all partial probabilities shown before, which can easily be calculated numerically using the expressions on the previous slide. The result is shown here. It looks very much like the P0 given before, but the difference is in the denominator, which contains now the energy of the resonance, ER, instead of the energy of the initial neutron, E. Actually, the result is not very surprising. We have just calculated in a slightly different way that the neutron flux depends on the reciprocal of the energy. The lower the resonance energy, the higher the neutron flux density and the larger the absorption probability. Till now, we have assumed that the resonance has a simplified rectangular shape. For real resonances, the expression changes to the lower formula on this slide, where the integral has to be carried out over the energy range of the individual resonance only. Note that the macroscopic absorption cross-section in the numerator is a product of the uranium atom density and its microscopic cross-section, while the total macroscopic cross-section in the denominator is a sum of the absorption cross-section of the uranium and the scatter cross-section of the hydrogen. How do the results till now influence the neutron spectrum? Previously we have seen that the neutron flux is inversely proportional to the energy, as indicated with the black dashed line on this slide. The reason that the neutron flux becomes higher with decreasing energy is the fact that the lower the energy is, the more multiple scattered neutrons can contribute to the neutron flux. If there is a resonance, the neutron flux below the resonance energy will also behave like a 1 over E, but with a little bit lower value because of the small fraction of neutrons absorbed in the resonance. This is indicated with the blue line. In general, the neutron flux in the presence of absorption resonances will show a 1 over E behavior, but with many small jumps at the resonance energies due to neutron absorption in these resonances. The neutron flux in the epithermal energy range below the resonance can be written as the unperturbed epithermal neutron flux with a 1 over E dependence, adjusted by the probability that the neutrons have survived the absorption resonance. This latter probability, indicated in red, is 1 minus the absorption probability and is called the resonance escape probability. Substituting the expression for the absorption probability given 2 slides ago, we get for the resonance escape probability the formulas on this slide. Because the value of the integral is usually very small, we can approximate 1 minus a small number as the exponential function. This is handy on the next slide, where we want to calculate the total resonance escape probability of all resonances in the epithermal range. The probability for a neutron to escape all resonances in the epithermal energy range is the product of the escape probability of each individual resonance. The product of many exponential functions, each containing an integral over the energy range of the individual resonance, can be written as an exponential function with the total integral over all resonances, as shown on the lower line on this slide. The last formula on this slide is the expression for the resonance escape probability of a reactor with hydrogen as a moderator. Like we did previously, we can decompose the total cross-section in the denominator as the sum of the absorption cross-section of the uranium and the scatter cross-section of the hydrogen. If the uranium density becomes very low, such that the uranium absorption cross-section in the denominator is much smaller than the hydrogen scatter cross-section, we can neglect the absorption term and simplify the formula to the expression on the lower line on this slide. The term before the integral is 1 divided by the scatter cross-section per absorber atom, and the integral is now the resonance integral of the absorber nuclide. This is the effective microscopic absorber cross-section of a uranium atom in a typical 1 over E epithermal neutron flux. If we use a moderating nuclide different from hydrogen, the resonance escape probability must be corrected for the fact that the average energy loss per collision is less for heavier nuclides. Therefore, we multiply the moderator scatter cross-section with the mean of the logarithmic energy loss per collision, indicated with the Greek character psi. This is indicated in red in the upper formula. The exact definition of psi is shown by the lower formula on this slide. It is the average value of the logarithmic energy loss per collision. For hydrogen, psi is unity, while for other moderating nuclides, the approximation in blue can be used. Here, capital A is the atomic mass of the moderator expressed in units of neutron mass. This table shows the value of psi for different moderators. It is seen that the approximation for psi, indicated again in blue, agrees quite well with the exact value for moderators heavier than hydrogen. The concept of psi is closely connected to a parameter alternative to energy, called lethargy. The lethargy of a neutron is a difference between the logarithm of a reference energy and the logarithm of the energy of the neutron itself. For the reference energy, an arbitrary high value is chosen, usually 10 to the 7 electron volt. Note that a neutron that loses energy actually gains lethargy. The use of lethargy is especially useful for the study of neutron moderation processes, because at each collision, a neutron loses on average a constant fraction of its energy, which implies that its lethargy increases on average with the same amount in every collision. From the definition of lethargy, we can derive that du dE is 1 over E, as shown in the left formula on this slide. And for the neutron balance must hold phi E dE equals phi U du, as shown on the right hand side of this slide. From these two expressions, we can derive that the flux per unit lethargy phi U equals E times the flux per unit energy phi E. In this plot, I have shown a neutron spectrum, which is the flux per unit energy of a light water-cooled nuclear reactor with uranium oxide as a fuel. The temperature of the moderator is 293 Kelvin in this case. This is sometimes also called room temperature. The spectrum along the y-axis and the energy along the x-axis are both given on a logarithmic scale, which makes it difficult to read because both scales cover so many decades. Therefore, it is quite customary to plot the product of the energy and the neutron spectrum versus the neutron energy. The y-axis now covers much less decades, which makes it easy to read, and the spectrum can now be studied in much more detail. The spectrum roughly covers three areas: the fast neutron flux above 100 keV with a shape dominated by that of the fission neutron spectrum, the thermal neutron flux below 0.5 electron volt with a shape dominated by a Maxwell-Boltzmann distribution, as explained in the lecture about the thermal neutron flux, and the epithermal energy range in between with the 1 over E energy behavior. Note that the perfect 1 over E behavior would give a horizontal line in this plot, as indicated with the blue line. The red curve deviates from a perfect 1 over E shape because of the resonance absorption of neutrons in the uranium of the fuel. Especially uranium-238 has a very strong resonance at 6.7 electron volts. Because the y-axis now covers much less decades, it can also be plotted with a linear scale. This looks like the figure on this slide. Some aspects of the neutron spectrum can now be seen even better. Here I've plotted the same spectrum together with the flux per unit lethargy on the right axis and the lethargy on the upper axis. The red curve shown on the previous slide and the blue curve shown here are exactly on top of each other, which indicates that E times the flux per unit energy, shown on the left axis, is exactly equal to the flux per unit lethargy, shown on the right axis. Furthermore, this plot shows that the energy on the logarithmic scale is identical to the lethargy on a linear scale. From this plot, the ratio of broad group fluxes can easily be derived, because the plot shows a flux per unit lethargy versus lethargy both on a linear scale. The area under the curve is therefore equal to the total neutron flux. Because the area under the curve above 100 keV, right of the red line, is slightly larger than the area under the curve below 0.5 electron volt, left of the green line, it's easily seen that the fast neutron flux is slightly larger than the thermal neutron flux. However, one should realize that the number of neutrons in the thermal energy range is much larger than the number of neutrons in the fast energy range, because the velocity of the neutrons in the thermal energy range is 1000 times less than the velocity of the neutrons in the fast energy range. So despite the fact that the fast neutron flux is slightly larger than the thermal neutron flux, almost all neutrons have thermalized and they keep on bouncing with moderator nuclides until they leak away or until they are finally absorbed by the fuel nuclides or by the structural materials in the reactor core. From the mean logarithmic energy loss per collision, previously indicated with Xi, we can now easily derive the average number of collisions needed for a neutron to slow down over a certain lethargy range. This number is just the lethargy range delta U divided by the Xi of the moderating nuclide. For a neutron to slow down over a lethargy range of 15, which for example corresponds to slowing down from 1.35 MeV indicated with the red line, 2.4 electron volt indicated with the green line, on average 15 collisions are needed with hydrogen, 21 collisions with deuterium, or 95 collisions with carbon as a moderator. We will finalize this lecture with a number of conclusions. First, the fission neutron spectrum is described by a Maxwell-Boltzmann distribution with a temperature of 1.6 times 10 to the 10 Kelvin. Alternatively, the Cranberg fit can be used. Secondly, the epithermal neutron spectrum with no absorption and no leakage and with a constant scatter cross-section shows a 1 over E energy dependence. Third, the resonance escape probability gives the fraction of the epithermal neutrons that have survived all fuel resonances. And fourth, the neutron spectrum is most clearly plotted as a flux per unit lethargy versus the lethargy, both on a linear scale. In the energy domain, this means plotting E times phi E versus the energy on the logarithmic axis. Thank you for your attention, and if you have further questions, please contact us at one of the websites shown here.